Let's continue with talking about cyclic groups with an example. So remember, a group is cyclic if there exists an element, there could be more than one, but at least one element, lowercase g is what I'm going to call the element, such that the subgroup generated by g, this lowercase g, which means all the powers of g, equals the group g. So first of all, what do the powers of this element g, lowercase g, mean? Well, if n is a positive integer, then g to the n is just g star g star g, where there's n copies of g, and asterisk or star is whatever the group operation is. If the group operation is addition, then you're adding. If it's multiplication, then you're multiplying. If n is 0, then g to the 0 is the identity element. Usually, the identity element is either 0 when the group is written additively, and 1 if the group is written multiplicatively. And then if n is a negative integer, then g to the n means you take g inverse, so that's g to the negative 1, and then raise that or multiply that absolute value of n times. Okay, so here are some examples of cyclic groups. The simplest example, maybe, is z with addition, and there 1 and negative 1 are generators. Why are they generators? Well, if you take all the powers of 1. Now here by powers, the group operation is plus, so it's really not quite powers how you'd ordinarily think of powers of 1, which is just 1, but multiples of 1. So all the multiples of 1 are all the integers. The negative multiples give negative integers. Then the integers mod n form another example. Again, the group operation is addition, and 1 and negative 1 are generators, but there could be some others. Let's see an example. So let's take a concrete example where n is equal to 10. Then z mod 10z, or z10, is the numbers from 0 through 9, and I'm claiming that 3 is a generator. So what is the subgroup generated by 3? Well, the group operation is addition, so we just have to add 3 to itself a bunch of times. So 3, 6, 9, then 12, but then we're working in mod 10 land, and so the 12 is the same as 2. Then I add 3 to the 2 to get 5, 8. 8 plus 3 is 11. I care about the last digit because I'm working mod 10 land. And then 4, 7, and then finally 0. Once I'm at 0, I'll add 3 to 0, you get back here. Okay, so it turns out that we get all the elements of Z10. That doesn't always happen. For example, it won't happen for 4. But just to finish up with 3, this means 3 is a generator for Z10. And so Z10 is a cyclic group. Well, we already knew that because 1 is a much simpler generator. But 3 is another generator. And so like I said, that there could be other generators. Okay, but 4 is not a generator. What do I mean by generator? An element the subgroup it generates is the entire group. That's what a generator of the group is. And so let's look at the subgroup generated by 4. We just take multiples of 4. Again, multiples, not powers, because the group operation is addition. And so 4, 8, 12, which is same as 2 in mod 10 land. 2 plus 4 is 6. 6 plus 4 is 10, and 10 is 0 mod 10. And then going back, adding 4, we get back to 4. Okay, and so this is not all of Z10. And so what we see is that this element 4 generates a subgroup, a proper subgroup, it's not the entire group, of Z10 of order 5. Remember, the order of a subgroup is the number of elements it has. And the order of an element is the smallest multiple in this case, or power in general, where that gives you back the identity. So we have to take 5 copies of 4, add 5 copies of 4 to get back to 0. Also, the GCD of 4 and 10 is 2, and it's a general fact that the order of 4, which we found to be 5, is the same as 10 divided by the GCD. here's this theorem in general, is that in any Z mod n group, the order of an element G, so for in the previous slide we were taking G equals 4, but for any element G, the order is n divided by the GCD of n and G. So in the previous example, n was 10, G was 4, the GCD of 10 and 4 is 2, 10 divided by 2 is 5, and we saw that the order of 4 was 5. A corollary of this theorem is that the generators of Z mod nz, with again addition as a group operation, are those elements in the group such that the GCD of G and n is equal to 1. Because when the GCD of G and n is equal to 1, this denominator becomes a 1, and then the order of G becomes just n, and so then you generate the entire group. So in a concrete example, the generators of Z mod 10Z are 1, 3, 7, and 9, because these are the numbers that have GCD of 1 with 10. And we saw that 3 generates the group Z mod 10Z on the last slide. We computed all the multiples of 3, and we got the entire group back. So I won't prove this theorem right now. You can look at the textbook for the proof.